Hi, my name is Christian Royer. My partner is Adana Anderson. Our advisor is Dr. Liz Schlemmer, and our topic is implementation of smart grid technology at Cal Poly. Background and motivation. Energy consumption in the U.S. will increase by 47% from 2010 to 2035. In fact, U.S. will produce 25% of the world's greenhouse gases, even though we comprise only 4% of the world's population. And our current power grid has not had many large-scale innovation for the past decades. What this boils down to is we are going to continue to use a lot of electricity, and we need to work on being more efficient with our energy usage. When you turn on a light switch, the electric company will charge you at a rate of whenever you turn it on. For example, if you use electricity during peak hours, you'll be charged at a rate that is higher than non-peak hours. Energy during peak hours is mostly generated using hydrocarbons and is rarely renewable energy. And during off-peak hours, there is not enough demand to meet the minimum output for an energy company. So basically, there's a lot of wasted energy during off-peak hours. Some problems with this is one, that is more costly, and two, that is also inefficient. If Cal Poly, businesses, and residential areas start using a lot of electricity during peak hours, the energy company needs to work harder to generate this electricity that is demanded. This can cause blackouts in the area.
For our project, Adana will be handling the implementation and design layout of the smart grid technology, while my part will be to design a tool that we'll be able to use to figure out when is the most beneficial time to release the energy for our storage devices.
Next, I'll be talking briefly about one way you can store energy with the smart grid. During off-peak hours, you will store the energy in a battery. This is because it is cheaper to generate electricity during off-peak hours since there is less demand. Then during peak hours, you will release the energy from the battery and start using it for any appliances or other electricity needs you have. This way, you are using the energy you created during off-peak hours, which costs a lot less.
Hello, my name is Adana and I'm in the MS-ITM program, and I'm going to go ahead and go into how the system works. So as you guys can see here on the right is the 120 volts AC, and that is actually the power that comes from the grid from the house. All electricity comes out at 120 volts AC. Next you have the AC to DC converter, because batteries only charge on DC current, so this is here to change the AC that's coming from the wall to make it suitable to charge the battery. After the AC to DC converter comes the charge controller. This device is actually used to make sure that the battery does not deeply discharge or overcharge, both of which can damage the battery greatly and lower the lifetime cycle of the battery. After that is the timer, and the timer is used to make sure that the battery is only charging during off-peak hours, so you can set the timer, which is actually just a switch that'll open and close based on the timing that you set for it. And then of course you have the battery, which is storing the energy that you are storing during the off-peak hours and using during peak hours. And then you have another timer, which allows it so that another switch just opens and closes based on when the peak hours are. After the timer, you have to change the electricity back into AC, because you're going to be powering the load, which in any cases, whether it be a house or a computer, all of those devices run off of AC.
Next, I'll be talking about the process about how we attempted to solve this problem. For this project, we used the plan, do, check, act method. First, we stated what our problem was, and that is we did not have a way to estimate how battery storage technology could reduce the annual energy costs at Cal Poly. So to accomplish this, I needed to gather data so I can make an accurate costing model. I needed to figure out how much PG&E charges Cal Poly for their energy usage, and I needed to see how much Cal Poly used so I can plan for the demand. During the check phase, I needed to look at the trends of Cal Poly's energy usage so I could build a model for costing. This meant I needed to look at the energy consumption by month, week, and even day so that I could understand how the peak energy charges went over a time period. Then with these energy trends, I could create a costing model and see which one would save the most money at the end of its life cycle. For our plan step, we needed to define the criteria for what aspects of the battery storage system we wanted to test. First, we wanted to test the different battery storage sizes so that we could see if it'd be worth it to invest in a higher priced system to reduce more energy usage at Cal Poly. Then we wanted to see what would be the best way to utilize these storage systems so that annual savings would be the highest. The systems we wanted to look at were reducing the energy usage by a 2-hour peak demand during the entire peak hours, or a system that would be able to estimate when the peak was going to happen, and I will touch on more of these systems later. During the do phase, I needed to gather necessary data from PG&E and Cal Poly so I can start working on my model. For energy usage, PG&E has two major charges. your demand charge, which is in kilowatts, and your energy charges, which is in kilowatt hours. In each of these fields, there is a certain rate that you are charged depending on the time of day, max peak, part peak, and off peak, and the time of year, summer, which is more expensive, and winter. Every 15 minutes, PG&E takes a snapshot at the amount of energy you are using and records this info. The demand charge is the highest usage PG&E has recorded for that month. So let's say you have a monthly usage of around 3,000 kilowatts. If it jumps to 5,000 kilowatts, even if it's just once during the month, you will be charged at that rate. As you can see below, the max peak demand charge is $14.03 per kilowatt, while off-peak is $3.04. This difference in pricing shows the biggest potential savings would be to reduce the max peak demand. During the check phase, I needed to analyze the trends of Cal Poly's energy usage so I could see when the biggest opportunities to reduce the energy usage to save money were. From the facilities department at Cal Poly, I was given a year's worth of PG&E data. This consisted of 15-minute interval snapshots over a year's time, which added up to 35,000 data points. I separated the data by month in Excel and started to look for any similarities I could. One thing I noticed is that many of the peaks were during similar times per month, but not necessarily between months. For example, in April, the peaks were mostly around 1 p.m. to 3 p.m., but during January, the peaks were during 5 p.m., so it changes from month to month. I also looked at the trends over a day's usage. As you can see on the charts, the energy usage mostly follows a cycle pattern. With the month of October, most of the peaks occur around 1 p.m. to 2 p.m. This showed that I could potentially set up a system that would release energy during the same time interval each month, and I would be able to reduce a lot of the peaks. After analyzing the trends, I needed to put my systems to the test. I tested each system over the same energy usage data I received from the facilities department to see which would save the most money. The first system I tested was releasing energy over the same 2-hour period each day. I would change this 2-hour window based on which month I was in. For example, since January had peaks mostly at 5 p.m., I would release the energy starting at 4 p.m. to cover most of the peak. I was attempting to make an educated guess on where the peak would be so the system would reduce it. This can prove to be difficult because if the peak lies outside this window just once during the month, the demand charge will not be reduced. The next system I looked at was releasing energy during the entire max peak period, which is from 12 p.m. to 6 p.m. during summer months. Here you can see an example of the 5,000 kilowatt system and what it would look like. While the peak does not drop by much, this system ensures that the entire peak is reduced so that the max peak charges will be reduced even if there are 2 peaks at the opposite ends of the spectrum compared to the 2-hour window of the previous system. The last system we wanted to check was a system that would be able to automatically see when the peak was going to happen so it would know to start releasing energy to avoid a higher charge. While creating this would be difficult because you would need to know ahead of time what your energy consumption would be, we wanted to compare this system to the others to see what the cost savings would be. Here you can see what the annual savings would be if each system was implemented into Cal Poly, and there were some important results that I wanted to focus on. For the 2-hour system, you would save money on your energy bill, but many of the months ended up costing you more. This is because we estimated a 75% efficiency rating when storing and releasing energy from the battery, according to a study done by Black and Veatch. Since the energy is only being released during a 2-hour window, if there's any peak that lies outside our estimate, it would raise the cost for our demand charge. This proves to be difficult because the peak hour can fluctuate throughout the month. This can be because the weather changes, so more heating or cooling, or any kind of special event that could raise or lower the energy usage. The whole peak for the most part was able to reduce the energy cost by a significant amount because it was able to cover a wider range of times. Even if it doesn't reduce the energy consumption by as much as a 2-hour peak, the fact that it was able to flatten the curve leads to a lower demand charge overall. The estimating peak system was able to lower the cost by the most amount since it's able to release energy during the max peak times per day, rather than a fixed estimate per month like the 2-hour window. After a 10-year payback period with a 6% annual interest rate, these are the following returns you would get on each system. According to a study done by Black and Veatch, the cost for a high-energy storage deep cycle battery can be estimated around $2,000 per kilowatt, which would leave us about $3 million and $10 million for our 15 kilowatt and 5,000 kilowatt systems respectively. You can see that the payback period is not close to the investment costs it would be to implement these storage devices at Cal Poly. While I was able to create a tool to use for calculating the amount of cost saved with using a battery storage system, the cost of investment meant that you would be losing money over time. For future studies on this topic, an emphasis can be placed on any type of government subsidies that can lower the cost of investment in battery storage. There can also be future studies done on if there's another efficient way to release energy into the grid so that max demand can be lowered and they can lower the price overall. Another topic would be to look at the environmental benefits of storing energy during off-peak hours. In a state like California, where only 2% of our energy comes from coal, battery storage can potentially be a good way to use renewable energy. And lastly, looking at the cost impacts of where we would store this system at Cal Poly. Thank you for watching my presentation, and I look forward to speaking with you about it next week.